All right, guys, good morning. Give me a couple more minutes to start. All right, okay, let's start. Can you guys hear me and see my screen clearly? Sorry, I don't have my usual setup today. So can you just speak louder?
Yeah, looks good.
Okay, good, looks good. Okay. Okay, so let's start. Still trying to get my other desktop computer to join, but I can't seem to. Let's just check. Okay, so it's being recorded. Okay, will you please alert me if somebody is in the waiting room waiting to enter? Okay. All right, very good. Thank you. Okay, so this is where we were last time. So let's have a quick recap of where we were. So we want to, so P2 of RD, this is my space of all probability measures on RD, which have finite second moments. And our goal is to think of this as an infinite dimensional Riemannian manifold. That's the geometric construction that we are heading towards. Now, in order to do this, we started with a definition of what are smooth curves. And smooth curves over here are what are called absolutely continuous curves. Now, the absolute continuous curves have a certain definition, but the important part that you should remember here is that they are solutions of continuity equations. So if I have an absolutely continuous curve, so if I have absolutely continuous curve rho t, this is absolutely continuous if I look into W2 distance between rho t and rho s. and that's bounded by some integral g of u du from S to t for some g in L1. For some integrable g function, the W2 distance can be controlled. This is not particularly helpful in general. So there's an alternative characteristic which is given by their solutions of continuity equations, del t rho t plus divergence of vt rho t is equal to 0, where this velocity field vt is in L2 of rho t. So this is my alternative characterization of absolutely continuous curves. Now, one second. All right. So now there are lots of infinitely many velocities, in fact, that gives rise to the same continuity equation. But there is only one which is unique, which is the tangent velocity. And what is a tangent velocity? The tangent velocity is the one which lies in the closure of L2 of rho t of the gradients of smooth functions. So this is what I usually refer to as the gradient type. So if your function is already of the type of a gradient, this is the tangent velocity. Otherwise, you look into some gradient type functions, approximated by a gradient type function. If you insist that your velocity is gradient type, then you get that this is actually the tangent velocity and therefore unique. One second. Sorry, somebody is waiting at the. One second. Hold on.
I think you might be able to disable the waiting room in the meeting settings so that you don't have to add people.
Yes, but this will have to be done. I'll have to close Zoom and then reset the settings. So let's continue with this particular setup, and then the next time I should be able to do this. I think actually I cannot do this because I think University of Washington now requires Zoom to have waiting rooms. I will not be able to do this. Okay. So anyway, so for now I have added people here, and I've also joined from my. All right. Okay. I think this is better. Okay, good. So I could log in through my desktop so I can see if anybody's in the waiting room. All right, okay, good. So where were we? We were saying that there's a unique tangent velocity, and this unique tangent velocity is of the gradient type. And continuity equations can also be seen. They are the family of marginal distributions of a stochastic process where you sample the initial position according to rho naught, which is the initial point in this curve. And then you flow according to some smooth trajectories where the time derivative of xt is given by the velocity field vt of xt. And then the law of xt then becomes rho t. Good. So this is what we learned last time. This gives a full definition of what it means to have smooth curves in the Wasserstein space. Now, our main goal today is to talk about the Benamou-Brenier theorem and some of the other consequences of these definitions. So what is the Benamou-Brenier theorem? By the way, any questions on these definitions? I'm just doing a recap from last time, but is there something that you found confusing that you would like me to go over again?
I have a question.
Yeah, go ahead.
So these rho t's wrote here are supposed to be densities, correct, of the measures themselves?
Well, Not necessarily. So this one, roti, if their densities, they're fine, but this PDE is being satisfied in the weak sense.
Oh, I see. Okay.
So they don't actually have to be densities. If they are densities and the densities are smooth, you can ask the PDE to be solved in a strong sense where you actually take derivatives. But really what we are asking, if you recall from last time, is that if you take a smooth test function and if you take derivatives, then those are actually well defined. In fact, let me just go back to this. Right, so over here, over here, you see? So all we are really asking is that you take a smooth test function and you integrate with respect to this measure. Of course, there is a abuse of notation that's happening here, which is common in optimal transport, is that we don't differentiate between the notation of a measure and a density. So when I write this integral, I have integral with respect to the measure. And then you take a time derivative, and then I get this. Okay, so this
Okay,
doesn't
I see.
require density.
Mhm.
The only place for the density, actually, much of the theory actually can be built without densities. The only place that a density would be used repeatedly is when I'm invoking Brunier's theorem, when I'm saying that there is a gradient of a convex function which transports a density to another measure. That's the only place where I'm using density, but otherwise, no.
Okay, I see.
So what is the content of Benamou-Brenier theorem? So Benamou and Brenier, these are named after two French mathematicians, Jean-David Benamou, who was a PhD student of Jan Brenier. And this is a theorem from the late 80s. And it says the following. This is kind of motivated by Riemannian geometry. So I'm talking about I have this probability measures with finite second moments equipped with a Wasserstein 2 metric. Then I've also talked about geodesics. I've also talked about lengths of curves. How do these fit together? If this is a true Riemannian setting, I should be able to recover the metric from the length of the geodesic, or rather, in this particular form, recover the metric square from minimizing what is called the energy. And this is a common thing in Riemannian geometry, and we see this theorem also holding true for the Wasserstein space. So let's go over this quickly. So imagine that I have an absolutely continuous curve of probability measures, and I'm writing rho t vt over here to specify that vt is my tangent velocity. If I don't write vt, it could be arbitrary velocity, but I'm specifically writing rho t vt. That means that this is really the tangent velocity. Now I can define the length of this curve. What is the length of this curve? Remember, there was a concept of what was called metric derivative. And so the length would be, just like in the Euclidean setting, the length of the curve would simply be the integral of the metric derivative from time 0 to 1. My curve is going from time 0 to 1. We also established a result that the metric derivative is also equal to the L2 norm of the tangent velocity. And so the length of the curve may also be interpreted as the integral from 0 to 1 of the kind of this L2 norm of the velocity from 0 to 1. Okay? Recall that this metric derivative was defined this way. This was like the limit as h goes to 0, W2 of rho t plus h divided by absolute value of h. This was the metric derivative. And you can clearly see why this is a nice way of defining the length of the curve. This is how you would do even in the Euclidean case. Another notion of a path is that if I'm given a path, I can define the kinetic energy. This is my kinetic energy to be the integral of 0 to 1, the L2 norm square of dt. So this is just the norm. This is just the norm square. Okay. The Benamou-Brenier theorem would say that if I fix two endpoints, one is mu and the other is nu, then the W2 squared distance is actually given by the infimum over all the energies of all paths which are absolutely continuous that starts from mu and ends at nu. Good. It is also true that the W2 distance is given by the minimizing of the length of all the paths from between rho mu to nu. But typically people deal with this energy function. This is the more useful, this is the more convenient one to work with because it involves a square there. And that's what the Benhamou-Brigny theorem is saying. That it's saying that the squared distance is the infimum over all absolutely continuous paths rho that starts from mu and ends at nu, and you look into the infimum of all kinetic energies. Is the statement clear? Okay, so I have mu, I have nu, I can draw lots of paths joining mu and nu. But there is one path which in Euclidean case would be a straight line. That's my geodesic. And that geodesic is the one that's going to be my length minimizing curve. Okay, what did I do here? This length minimizing curve, this is going to be my geodesic. And this is the same thing which will minimize both the energy and the length of the curve, joining mu and mu in Euclidean setting. And this is also going to be the same thing for the Wasserstein 2 square. All right, we'll come to the proof of Benhamou-Brigny, but let's see, inherent in the statement over here, there is what I'm saying here is that the path that minimizes the energy is given by what is called the constant speed geodesic, or as we know from our previous discussion, this is the McCann interpolation between mu and nu. Okay. So, so the back to geodesics, the fact that both the energy and the length, they are minimized by the McCann interpolations. These are the geodesics, as we have already talked about it. So recall from this idea that what is my McCann interpolation? If I have my mu, if I have a mu and I have nu, now assume that mu actually has a density. These actually don't quite depend on this, but for simplicity, let's assume that mu has a density. Then there is a gradient of a convex function t such that t will push forward mu to nu. And my McCann interpolation, rho t star, is going to be the push forward of identity. So is going to be the push forward of 1 minus t identity plus t times capital T push forwarding me. Is that my McCann interpolation? And we learned a fact about McCann interpolations that if for a McCann interpolations, if I look into the distance between rho t star and rho s star in W2, that's exactly equal to t minus s W2 distance between mu and nu. I had mentioned this fact. If you don't remember it, please go back to the notes, or you can just try to prove it. It's actually quite easy to prove if you take s to be 0 and t to be something just in between. It's a little bit more complicated to prove for arbitrary s and t. But once I have this fact, what is my metric derivative? Well, the metric derivative, I will take this object, I will divide by t minus s and take a limit. So my metric derivative is actually constant, and it is given by W2 of mu and mu comma nu. What is the metric derivative supposed to represent? It's a speed. It's the size of the velocity, and therefore it represents the speed. And so it's saying that the speed is constant. That's why it's called a constant speed geodesic. And therefore it will satisfy, because this is absolutely continuous, this is clear from here that this is absolutely continuous. As you can see that this is just multiple, it's actually Lipschitz with a Lipschitz constant of W2 mu and nu. So it is absolutely continuous, and it satisfies the continuity equation, which is del t rho t star plus divergence of Vt star rho t star is equal to 0 for some choice of Vt star. Now, because the L2 norm of Vt star must coincide with the metric derivative, I also get that the L2 norm of Vt star is equal to W2 of mu and nu. You can also directly verify it from here, from this definition. Does this make sense? So what I have here is that I have defined my constant speed geodesics, which is my Macan interpolation. This is what we did last time. That gives you a curve of probability measures joining mu and nu. This is supposed to represent my straight line. And what is a property of the straight line? Well, it has two properties. One is that, okay, I'm traveling along a straight line, so it's constant speed. There is no acceleration here. So I recover the same fact here. And that, and not just that, but then also it minimizes the energy. It minimizes kinetic energy among all paths joining mu and nu. And that's a statement of Benamou and Bernier. Good. All right. Okay. Any questions on this? Good. You guys can hear me clearly, right? I don't have my usual setup, but just want to make clear that you guys can hear me clearly. Okay, good. So how do I prove the Benamou-Bernier theorem? Again, the proof is actually quite easy. It's just an application of Jensen's inequality. There is some technical details here which I'm sweeping under the rug, but the main idea is just a Jensen's inequality. But it's a beautiful proof, so let's go over this. So suppose I'm given some absolutely continuous curve which joins mu and nu. Because it is absolutely continuous, it must satisfy the continuity equation. And this is my continuity equation, del t rho t plus divergence of Vt rho t is equal to 0. Now, as I did in my recap and my last class, the continuity equation can be thought of as the sequence of marginal distributions of the following stochastic process. You sample x0 from mu, and then you have a differentiable path where the time derivative of x at time t is given by vt of xt, where vt is given from here. So remember, this is my tangent velocity. Actually, this is not particularly important here, but anyway, let's assume this. But this is not really important in what comes here. The energy of rho, by definition, is given by this. This is the L2 norm of the tangent velocity squared, the rho tx dx. So let's go back here. This was my energy. I look into the L2 norm of the tangent velocity square, integrate from 0 to 1 dt. And that's exactly what is this definition is saying. The L2 norm square is nothing but the norm square of Vt of x integrated with respect to rho t of x dx. So the second integral is over Rd. Now, because I have a single stochastic process, I will do my usual trick, which is that I will represent this xt as a function of x0, right? Because xt has the law rho t, first I'm going to write, this is the expected value. I will switch these two integrals. And I will say this is the expected value of the integral 0 to 1 norm of Vt of xt norm squared dt. This makes sense? Anybody who is familiar with stochastic process means that I can construct on some probability space omega f p, I can construct this path of this stochastic process xt, t between 0 and 1. And on that probability space, all my random variables are supported. And therefore, this whole integral on the probability space can be written as expected value, integral over the path, a realization of the path of this process of norm square of Vt of xt. Are you guys following what I'm saying here? Good. And now what I'm going to do is that I'm going to do Jensen's inequality. So this inequality is due to Jensen's inequality. So I'm going to put this norm square outside. So what is Jensen's inequality I'm writing here? It's basically saying expected value of y square is greater than or equal to the norm square of expected value of y. Okay, that's just the fact that variance is non-negative. So here is expected this quantity, which is the norm square in the Euclidean space. This is a convex function. And so I can put the integral inside. So the Jensen's inequality is being applied for every path for the Lebesgue measure on 0, 1 as the measure, which is a probability measure. And so I can put this integral 0, 1 inside, and I get this is less than or equal to expected value norm square of the integral 0 to 1 vt xt dt. Good, good. So the energy of rho is always greater than or equal to this quantity. Now, how do I get W2 square? It's very clever. So what you see here is that this stochastic process where I sample x0 from mu and I follow the smooth path x dot t is vt of xt. So I'm getting x0 and I'm sampling this thing until I get to x1. So what is my law of x1? Well, by definition, the law of x1 is nu and x0 is mu. But this actually gives me a transport map that sends mu to nu, an explicit transport map. What is a transport map? X0 is being sent to x1, where x1 is x0 plus the integral of the velocity vt xt dt. By definition, my stochastic process, by definition, if I follow my path of the stochastic process, it's sending my initial measure mu to my terminal measure nu via a path that is smooth and therefore a nice transport map. And therefore, if I follow that path, what is my cost of transport? Well, there's a difference between x1 and x0, this guy and that guy, which is this integral, 0 to 1 vt xt. And so the expected value of the 0 to 1 vt xt dt norm square must be at least as large as w2 square mu to nu. But now I claim that this w2 square mu to nu is also the energy of the constant speed geodesic. And thereby, if I accept that, then thereby I get that energy of rho must be greater than or equal to energy of rho star, and therefore energy of rho star, which is equal to W2 star of mu and nu, and rho star is the one that is minimizes this. All right. Let's go over this again. It's a very clever proof. So in one swoop, I'm going to prove the following. So let's go back to the proof statement of Benamou and Bernier. So Benamou and Bernier is saying that consider any mu and nu, consider all absolutely continuous curves which starts at mu and ends at nu. For each one of them, you consider this energy, and then you minimize the energy among all such paths. Then this infimum of all this energy is exactly the W2 squared distance. This is not rho and rho 1 and thing. This is mu and nu. The W2 squared distance between all such paths is exactly W2 squared of mu and nu is infimum of all the energy. And that this infimum is actually attained at the constant speed geodesic or the Macan interpolation joining mu and nu. That's the first statement that we are proving. And how does the proof go? Let's go for this again. Take any absolutely continuous curve that joins mu and nu. Then that absolutely continuous curve satisfies the continuity equation del t rho t plus divergence of vt rho t is equal to 0, where vt is my tangent velocity. Once I have this continuity equation, then I know that I can replicate the solution of this continuity equation by constructing a stochastic process where I sample the initial point from where I start from, which is mu, and then I move along a smooth path where the time derivative of xt is exactly equal to the velocity vt applied to xt. Then the law of xt is rho t. This lets me do several things. If I write down what the energy is, then the energy is this by definition, is the integral of vt square rho tx dx, integral over space, integral over time 0. But now I have a whole stochastic process. So with respect to the expectation of that stochastic process, I can flip this integral between bring it to integral here, and this becomes expected value, integral of 0 to 1, norm square of vtxt dt. Now I use the Lebesgue measure on 0 to 1 as my probability measure, the norm square as my convex function, And for every realization of the path of xt, I apply Jensen's inequality. When I apply Jensen's inequality, the norm square and the integral, they switch places, and I get an inequality. This is the expected value of 0 to 1 vtxt dt norm square. And now you observe something very clever, that this stochastic process that has smooth paths is actually giving me a transport map from mu to nu. What is a transport map? x1 is exactly equal to x0 plus integral of the velocity vtxt dt from 0 to 1. What is the cost of this transport? Well, it's the difference between these two, so it's expected value of norm square of this integral. But by definition, the W2 square distance is the infimum of all such transport maps, and therefore this is true. Now, the whole setup is actually also true if the corresponding absolutely continuous curve is my Macan interpolation. But for that Macan interpolation, the norm square of Vt of x dx is constant, the L2 norm square. What is that constant? Is W2 square. And so its expectation is also this thing, and therefore the energy of Macan interpolation is just W2 square. And thereby I recover that the infimum over all absolutely continuous curves gives me the Wasserstein 2 square distance, and it is actually attained at the Macan interpolations. Let's hear from you guys. Did you guys follow the argument? Is there something I should go over again? Okay. So again, yeah, go ahead.
So the rows really have to be absolutely continuous?
So, so yes and no. So okay. So the geodesic is unique if mu is absolutely continuous. It's given by the Macan interpolation, given by the Brinier map. If your mu is not absolutely continuous, there are multiple geodesics, but they are not unique. And so there are multiple solutions to this. The theorem Benamo-Brinier still remains true, that this energy inequality is still true, but the minimizer is no longer unique because the geodesic is not unique. That's the only difference.
I see. Okay.
Okay. So the Wasserstein space is a geodesic space. Well, sorry, I'm getting it. So there are always geodesics, but they may not be unique. But they are unique if mu is absolutely continuous. Okay, any other questions? I again want to stress this fact that you are proving something about Wasserstein space. You should keep in mind that it always involves some kind of creating a stochastic process, creating some kind of change of variable and writing down everything in terms of the initial variable and then using this push forwards. This is always the technique that you use for proving any of these theorems. Any other questions? If you don't understand a part of this proof, then again, please let me know and I'll go over it. All right. Okay, good. So let's go to the next statement here. So differentiability of the Wasserstein 2 squared distance. So here is a theorem. Let rho t vt be an absolutely continuous curve with tangent velocity. So it satisfies my continuity equation, and then vt is of this gradient type. It belongs to this tangent space velocity. Assume that everything has densities. Otherwise, it's complicated. Let's assume everything has densities here. Now fix a sigma, which is some other element with second moment in Rd. Then almost surely in the interval 0, 1, this object, this map, which takes your t to W2 square, rho t to sigma, is differentiable at t. And derivative can be written in the following way, that the time derivative of 1/2 W2 square rho t to sigma is the L2 inner product between two quantities. One is the identity minus capital T of t. 1 second. Just give me 1 second, please. So I mean, it's C444. That's where Kavita's. Oh, C444. Yeah, so downstairs. Okay. All right, sorry about the interruption. So let's go over this again. So what is capital T of T? Where capital T of T is the Brownian map that push forwards rho T to sigma. Okay. So capital T of T is the Brownian map that takes push forwards this. Okay, hold on. Somebody else is in the waiting room. So let's see this, what this theorem is saying again. So I have a curve. I have a curve of rho T. I have a fixed measure sigma. At every point in rho T, I look into the squared Wasserstein distance. So this is the square of the distance from rho T. As my curve is changing, the squared Wasserstein distance is also changing. I am saying that this is differentiable almost everywhere. This is just a curve of real numbers. So this is differentiable almost everywhere. And the derivative is given by the following. It's the L2 inner product of the map identity minus capital T of T, comma Vt in the L2 inner product space. So what this means is that this is equal to x minus Tt of x, Vt of x, Euclidean inner product, rho T of x dx. How should I think of this result? You should think of this result in terms of a Euclidean analogy. So imagine that I have a Euclidean curve where x dot t is equal to vt. So that's my Euclidean curve. I fix another vector y, and I look into the time derivative of 1/2 norm square of xt minus y squared. Well, this is an easy peasy derivative. What do I get? I get this is equal to xt minus y dot vt. Right? So I have my curve xt, I have my y, and I look into the inner product of this difference, xt minus y, I take the inner product with my tangent vt. Now in the Wasserstein space, as I said repeatedly, it lifts Wasserstein geometry to the space of probability measures. So this vector that joins xt to y, which is xt minus y, is taken over by this element in the L2 of rho t, which is identity minus capital T of t. So capital T of t is push forwarding my rho t to sigma. This is nothing but the Kantorovich potential. I don't know if Young-Hun has used this word, but this is just a gradient of the Kantorovich potential. It's identity minus capital T of t. This is what appears in the duality of the Wasserstein 2 square. And so that takes place of the vector xt minus y, identity minus Brownian map. The Vt, which is the tangent to the Euclidean curve, gets replaced by the vector field Vt, which is the tangent velocity of this curve. And the Euclidean dot product gets replaced by the L2 inner product at the point rho t. But otherwise, this is exactly the same statement. So this is a mnemonic that you should always remember when you do Wasserstein calculus. Do the calculus for Euclidean space and do this kind of transfer of notations to guess what the corresponding results should be in Wasserstein space. They will not always work, but they will often work. Is the idea clear? Is the statement clear? Okay. So again, what I'm saying here is that I have an absolutely continuous curve with its tangent velocity vt. Assume everything has nice and smooth densities. I look into some another probability measure sigma, then almost surely there is a derivative of 1/2 w2 square rho t comma sigma, and that derivative is given by the L2 inner product at rho t of the map identity minus capital T of t, which is the gradient of the Kontsevich potential, and my time varying velocity field vt. All right, okay. Let's try to prove this. The proof is not difficult, and again, the proof is instructive, so let's try to prove this. I'm just giving the idea of the proof. There are some bells and whistles, but they're all pretty fairly straightforward to resolve. So first thing that you would notice here is that the map that takes time t to the Warschaschen distance of rho t to sigma, this is absolutely continuous as a curve in R on the real line. Right? These are all real. This is a curve absolutely continuous in R. As a curve on the real line, this is absolutely continuous. Why? Well, fix any 2 points S and T, which are not equal, then apply the triangle inequality for the metric, the Warschaschen 2 metric. This is a metric. And I get that the distance between W2 of rho T comma sigma and W2 of rho S comma sigma, by triangle inequality, this is bounded by the W2 distance between rho T and rho S, which is bounded by the integral of S to T gu du. Why? Because I've assumed rho T, this is absolutely continuous. It's an absolutely continuous curve of probability measures. Therefore, by definition, there will exist such an integrable G. Good. Now, once this is absolutely continuous, Rademacher's theorem will say that this is differentiable almost everywhere. So there is a null set outside of which, if I take time t in that outside of that null set, then this function t to the W2 distance between rho t comma sigma, or W2 square distance rho t comma sigma, this is differentiable at time t. Now, the other fact that I'm going to use is a fact that we talked about last time, which is that once you have an absolutely continuous curve and this tangent velocity, the curve is very well approximated by this tangent approximation. So the statement is that there exists some null set such that if time t is not in that null set, this differentiability holds, and the following tangential approximation holds. What is a tangential approximation? That if I have a curve rho t, and if I look into time t and time t plus h, I can essentially approximate the curve by a tangent between time t and t plus h. How? Rho t plus h is the value of the curve at time t plus h. The tangent is identity plus h times the velocity push forwarding rho t. And the W2 distance between these two guys is little o of h. Okay. Do you remember this result? This is something that we did last time. And we say that all absolutely continuous curves, if you consider its tangent velocities, then you can approximate the curve by this kind of tangential approximations. So there is a null set in 0, 1. Outside of that null set, two things happen. One is that this function is differentiable, and two is that this tangent approximation holds. We're going to work on that null, outside of that null set, where we are going to show that this theorem is true. That's my almost everywhere in 0, 1. You guys are okay? I'm not hearing anything, but please let me know if you can't follow something. Are you guys, did you guys understand what the structure is? So there's a null set where everything is nice, one is differentiable, and there's a tangent approximation. Okay, good. So Darren is giving me thumbs up. And the others, yeah, if you just let me know. If you follow something, let me know. If you don't follow something, let me know. It's already hard in a in-person lecture to figure out what the students are learning or not. It is extremely hard in the online class to figure out what students are learning or understanding. If you don't give me signals, I cannot read minds. So let me know. Okay, good. So now let's go to the proof here. So call rho hat of t plus h to be this map, this identity plus hvt push forward of rho t. So what is rho hat? This is my rho hat. This is my rho at time t plus h, and rho hat is where I will reach if I follow the tangent. Now for t, which is not in this null set, this derivative exists. Why? Because that's what one of the null sets property is. I said that this derivative exists, the derivative of this map exists, but in derivative of this map exists by chain rule, the derivative of the square of the W2 square distance that also exists. So this map, this derivative exists. By definition, this derivative must be given by the following limit. Is W2 square of rho of t plus h sigma minus W2 square rho t of sigma divided by h. By definition, that's the definition of the derivative. So that must exist. Now, because rho t plus h is well approximated by rho hat of t plus h up to an error of little o of h, then this also holds that I can replace rho t plus h by rho hat of t plus h, and this limit is also the same as a derivative. Right? The difference between these two guys is little o of h. And so I can replace rho t plus h by rho hat of t plus h, sigma, and that's h. Now, why am I actually using rho hat of t plus h? The reason I'm using rho hat of t plus h is again the same idea. I can couple everything by one single stochastic process. So what is a stochastic process? Sample your x from rho t. Now, if I sample my x from rho t, by my very definition, the law of x plus vt of x, this is exactly rho hat of t plus h. By definition, because that's what the push forward does. X plus h vt of x is rho hat of t plus h. Now, I have a x plus rho h of vt of x has rho hat of t plus h. By definition, tt of x has law sigma. So this has rho hat of t plus h. This has law sigma. And so I get a coupling of rho hat of t plus h and sigma by considering the pair x plus h vt of x and tt of x. This is an element of a coupling of rho hat and sigma. Right? This is an explicit coupling. Sample x from rho t, x plus h vt of x, that has law rho hat, and tt of x gives me sigma. So this is a coupling. So the norm square between this difference in this thing must be larger than no. So this must be larger than the W2 squared distance between rho hat of t plus h and sigma. Because W2 square, by definition, is the minimum norm square between all couplings. And I have exhibited one explicit coupling, so this must be smaller. Now, what happens if I open up the square? I'm going to combine this x with this tt of x. If I take this x minus tt of x norm square, by my very definition, this is W2 square between rho t and sigma. Why? Because tt of x is exactly my Brinier map that sends my rho t to sigma, and so x minus tt of x norm square is exactly W2 square. How about the inner product? The inner product between x minus tt of x and h of vt of x gives me this term. Twice h, identity minus capital T of t, and vt, L2 inner product. Finally, I have the term which is h square vt of x norm square, and that's because it's h square. This is actually a term which is little o of h. Are you following this? So W2 square rho hat of t plus h com sigma is less than or equal to W2 square rho t comma sigma plus this term that I'm actually interested in plus little o of h. Okay. Now, if I rearrange this term, I get W2 square rho hat of t plus h comma sigma minus W2 square rho t comma sigma is less than or equal to twice h, the inner product, plus little o of h. So there are two cases that you can do. One is h positive and the other is h negative. If h is positive, you divide both sides by h. This inequality is preserved. And I take a limit. I get that this is less than or equal to this quantity. On the other hand, if h is negative, when you divide both sides by h, the inequality is flipped. Now you take a limit and you say this is greater than or equal to this. And therefore, combined together, I get this equality. How are you feeling? Everything is good on this proof? You want me to go over this proof again? Okay. All right.
Yeah, could you explain the splitting it into the Wasserstein distance plus the inner product again, please?
Right. So I have this quantity here, which is the expected value of norm square x minus tt of x and plus h of vt of x norm square. So I expand the square. When I expand the square, I get the expected value of x minus tt of x norm square, plus I get some inner product term, and I get little o of h. So that's fine. Now, what is tt of x? tt of x, by my very definition over here, this is my Brunier map. Okay, so this is actually my Brunier map that transports rho t to sigma. What is a property of the Brunier map? What is the optimal transport map? And so if I look into this quantity, which is x minus tt of x norm squared, take the expected value when x is being sampled from rho t, this is exactly equal to the W2 squared distance between rho t and sigma. Does this make sense?
Yeah, thank you.
So that's what is being used here. So the way that is working here is that I'm cleverly picking a coupling such that the argument goes through. And this is always done by this push forwards. This is a repeated lesson here. Good. So again, two lessons here. One, I want to take this derivative, right? This is my quantity here. I want to take this derivative. And so I need to compare this quantity, W2 square rho t plus h sigma, W2 rho t comma sigma. Now they are both, now if I want to directly write down what is W2 squared, this is given by this quantity, by Brunier map. That is given by another quantity which involves the other Brunier map, capital T of t plus h. Now I don't know how these Brunier maps are being differentiable. They seem odd. I don't quite know. So what I do is that I simplify the problem by using my tangential approximation. Instead of working directly with this guy here, which has a different Brunier map that gives its different optimal transport, I work with the rho hat, which is in terms of the density at time t. This gives me a coupling. When this gives me a coupling of the type x plus hvt of x. So what the proof is essentially showing is that this coupling for very small values of h is essentially the optimal transport coupling from rho t plus h to sigma. This is approximately the Brunier map at time t plus h is being given by this. And so I use this coupling over here and I plug this in and I get this inequality by my optimization. And then this is an algebraic manipulation by taking h positive or h negative. that when I take the limit, I would get exactly this. Okay? But the underlying idea is that if I have an absolutely continuous curve, I have rho t plus h, all the Brinier maps are changing. Time t plus capital T of t plus h, they are changing. How do I keep track of them? The idea is that if h is very small, and if you have capital T of t for one point time t, the other one you can construct very well by simply following the tangent direction from t to t plus h, and then combining with the capital T of t that sends rho t to sigma. And that is approximately what the optimal transport map is. Is the idea clear? Okay. All right, good. So that gives us this theorem that this W2 square distance along an absolutely continuous curve is differentiable, and its derivative is given by this L2 inner product. How should I remember this object? Well, just go to the Euclidean case. In the Euclidean case, this derivative of the norm squared is given by xt minus y dot vt, where xt minus y is just this, the vector joining xt and y, and vt is the tangent. And use this mnemonic that the vector joining x and y should be replaced by the gradient of the Kantorovich potential, identity minus the Brinier map. And the tangent velocity of Euclidean curve should be replaced by the tangent velocity field of my absolutely continuous curve. And the Euclidean dot product should be replaced by the L2 inner product. And that's it. Okay. Now, the Euclidean analogy doesn't always hold. And the reason for this is something we haven't talked about it. We might talk about it later, is that the Euclidean geometry is a flat geometry, while the Wasserstein geometry has positive curvature. It's not a flat geometry. So here is one striking example of something that you would obviously anticipate from Euclidean analogy, but it's actually not true for the Wasserstein analogy. The squared Wasserstein distance function is not Jurassically convex. So what do I mean by that? If I fix my sigma, which is some probability measure, and I look into the map that sends mu to W2 square mu to sigma, this is not convex over the Jurassics. This seems rather unintuitive, because if I fix my y in my RD and I look into my curve, x being sent to 1/2 norm square of x minus y norm square, then this is obviously a convex function of x. This is simple Euclidean algebra that this is convex. But this is not true for the Wasserstein case. This is not Jurassically convex. Okay, that's crazy. You would obviously anticipate this to be true, but it's not. There is a deeper reason why this is true. We cannot quite get into the deeper reason, but it suffices to say this is because Wasserstein space is positively curved. There is some curvature involved here, and that's why it's not true. So let's go over a counterexample. The counterexample is instructive to see why this is not true. So I'm going to draw a curve mu t, which is like this. So this is my dimension d is equal to 2. By the way, everybody remembers what the notion of Jurassic convexity is, right? It means that if I take 2 points, mu0 and mu1, and I draw the constant speed Jurassic along mu0 and mu1, then this function restricted to that one-dimensional path is not convex in the usual sense, or may not be convex in the usual sense. So here is a counterexample to this. So, so t is taken between -1 and 1. This is just for convenience. You could just rescale everything to 0 to 1. So what is mu minus 1 and what is mu plus 1? So this is dimension d is equal to 2. Every mu t has 2 atoms. One of the atoms is at t2. So take t equals to time 1. T equals to 1. And so, so 2 is, let's say, here. So -2 is here. 1 is here. -1 is there. And so my terminal point, t equals to 1, has two atoms. The first atom is at 1, comma 2. The other atom is at -1, comma -2. Okay. Now, at time t equals to -1, it's at -1, comma 2, and at -1, comma -2. Sorry, -1, comma 2, and +1, comma -2. So over here. So these are my two atoms, two red atoms and two blue atoms. And now, how do I draw the geodesic line between them? Well, let's try to do an optimal coupling here. Now, from the geometric picture, it's actually very clear what the optimal coupling is going to be. The optimal coupling is simply going to transfer this red dot to this blue dot, and that red dot to this blue dot, and that's clear. That's when it's going to minimize the distance. But really, this is like atomic measures with two atoms. There are only two possibilities. Either this atom is sent to that atom, this atom is sent to that atom, or the other one. This atom is sent to this atom, and that atom is sent to that atom. Right? So either you go along the same y-axis or you do the diagonal case. The reason I've picked 1, -1, 2, and -2 is to make it obvious that the diagonal transport obviously has greater length. And so the obvious transport is going to be joining the red and blue atoms at y2 and the red and blue atoms at y -2. And that's the best matching that you can get. Is this clear to everyone? That's the best matching that you can get. So you should join these two guys, and you should join these two guys. And that preserves the masses, 1/2 and 1/2, and that's the best matching. And therefore, what is the mechanical interpolation? Well, I'll be moving along here. I'll be moving along there. And so at any point in time, I will have two atoms. One is t, comma 2, and the other is t, comma -2, or rather minus t, comma -2, with 1/2 and 1/2. And therefore, this is my mechanical interpolation or constant speed geodesic joining the two terminal measures. Is this clear? Okay. Now let's fix some sigma. So this is my geodesic. Let's do some sigma here. So my sigma is 1/2 delta at 1, comma 0 and 1/2 delta of -1, comma 0. Let's again draw a picture here. So my axis, so 2 minus 2 t minus t. So I have two atoms. So t comma 2, which is here. So if you look into mu t, t comma 2 and minus t comma -2. So if t comma 2, when t is positive, is right over here. Oh no, what did I do? So t comma 2, when t is positive, is right over here. And minus t comma -2 is right over here. When t is negative, I will flip their positions. And now what is my sigma? My sigma is 1, 0. So 1 is to the right side of t, so it's here. This is one atom. And -1, 0. So this is to the left side here. So this is the other atom. So this is -1, comma 0. And this is 1, comma 0. So this is my t, comma 2. And this is my minus t, comma -2. This is when t is positive. And I ask you, like, okay, what is the optimal transport between these two guys, these two atoms? Again, these are just two different atoms. There are only two possibilities. Either you send t comma 2 to 1 comma 0, minus t comma -2 to -1 comma 0, or the other way around, t comma 2 to minus t comma -2, -1 comma 0 to 1 comma 0. Again, from the picture, it is obvious that the diagonal transports are going to be much more expensive. So at least one of the diagonals. So the obvious transport is I should send t comma 2 to 1 comma 0, and I should send minus 1 comma 0 to minus t comma minus 2. Is this clear to everybody? I'm saying it's obvious, but this is a fault of all math professors saying that, oh, things are obvious when they're not. Good. Okay, so when t is positive, what is the optimal transport cost? Well, the optimal transport cost is t minus 1 square plus 4, which is from these two guys, and so that's 1/2, plus the other half, which is 1/2, minus 1 plus t. So again, another t minus 1 square plus 4. And so the total cost is t minus 1 square plus 4. But the situation, this is the Washington 2 square cost when t is positive. But the situation completely flips when t is negative. When t is negative, your t comma 2 is on this side of the board. So this is minus t when t is negative. This is plus t when t is negative. And so t comma 2 is over here. And minus t comma minus 2 is over here. And in this case, when t is negative, what do I get? My optimal transport cost again is now going to send these two guys. Minus t comma minus 2 should go to 1, 0. And t comma 2 should go to 1 minus 1 comma 0. And if you do this calculation, you will see this is 4 plus t plus 1 square. Right? T minus minus 1 is going to t plus 1 square. So I have two different cases. When t is positive, I get t minus 1 square plus 4, which is convex in t. When t is negative, I get t plus 1 squared by 4, which is also convex in t. But the full function, which is mu t comma now, is now 4 plus the minimum of t minus 1 square and t plus 1 square. And so this is the minimum of these two convex parabolas, and this is not convex anymore. And so this is not convex anymore. And that's the whole reason why I shifted my time. Again, you can do the whole thing from 0 to 1 as well. That's not the problem. The problem is how the atoms are shifting in space. Yeah. So there's a concrete example, and again, play around with examples, come up with your own. This is, with two atoms, this is not particularly hard. If you put these points in some space, in some specific order, then you can find geodesics where this squared Euclidean cost function is not convex. And as I said, this is rather surprising. Is the counterexample clear? Okay, good. More surprisingly, this actually is convex for some generalized geodesics. And this is again where you see that sometimes generalized geodesics are actually more useful than just using geodesics themselves. So the squared Washington distance is convex if you draw a different curve between mu and nu, which is not the geodesic, but the generalized geodesic based at sigma. So here is the statement. So fix your sigma, this is also absolutely continuous, as base for my generalized geodesic. And now you look into rho t, which is a generalized geodesic with base sigma. Now this is a curve that joins rho 0 to rho 1, which is base is at sigma. This is not their geodesic, this is not their Mecan interpolation. Now along this curve, then the function t going to 1/2 w2 square rho t comma sigma, this is convex. Of course, 1/2 is not really necessary. I just carry it on because this is a convenient constant. So if you're computing the convexity from a fixed measure, you should use generalized geodesic based at that fixed measure, and then this becomes convex. And I'm going to prove it. The proof is again instructive and easy. But there is some curves along which this is convex, other curves it is not convex, and this kind of fails our Euclidean analogy. Good so far? Okay, let's go over the proof. So the proof of generalized geodesic convexity goes like this. So what is a generalized geodesic line? So recall that a generalized geodesic is given by this. So I have my rho naught, I have my rho 1, and I have some base sigma. There is a map, the Brownian map, that takes sigma to rho naught, which is given by T0, some gradient of subconvex function. There is a Brownian map that goes from sigma to rho 1, that's T1. That's my Brownian map from sigma to rho 1. And my generalized geodesic, rho t is 1 minus t0 plus t times t1 pushed forward by sigma. And so that's what gives me my generalized geodesic here. Good. By the way, I have to ask this question. On the Euclidean setup too, I can consider a generalized geodesic. What happens to generalized geodesics in the Euclidean setting? So supposing I have 3 points here, I have x here, I have y here, and I have a base here, z. What do I get for a generalized geodesic? Is there a way to construct a generalized geodesic joining x and y with base z?
Is it just a circle centered at Z?
Why would it be a circle?
I don't know. I was just
No, but think about it. Like,
would be
just if
comfortable.
you try to make an analogous definition, what would your definition be? So what I mean, if I'm looking into like some kind of analogy, what would your definition be? Anyway, I'll leave it to you to verify that this will just give you the geodesic. It will just give you the same straight line, x be connecting between 1 minus tx plus t times y. There is no difference between them. Euclidean space is flat. There is no difference between them because the idea of generalized geodesics is coming from the Hilbert space, which is the L2 Hilbert space. At sigma, they give you the same thing for all Euclidean cases as well. They're just the same line. So the idea of this geodesic straight line is both geodesic as well as generalized geodesic for any base in the Euclidean case. And so you don't see this property. But when you have this curvature, as in the Wasserstein space, these are different distinct concepts. And the Wasserstein 2 square distance is not convex in the usual geodesics, but if you take a base at sigma, then it recovers convexity. And let's try to prove this. So this rho t is given by 1 minus t t0 plus t times capital T1, this push forwarding sigma. And so now if I sample my x from sigma, from my base measure sigma, and if I look into W2 square rho t from sigma, I have a natural coupling. What is a natural coupling? Well, x is from sigma, and 1 minus t t0 of x, t times capital T1 of x is from rho t, right? This is exactly what this is saying. 1 minus t t0 of x plus small t times T1 of x. This is from rho t. So I have a very natural coupling of sigma and rho t. And so W2 square, by very definition of being with the optimal coupling, must be smaller than whatever is the cost of transport according to this particular coupling. What is the cost of transport? 1 minus t t0 of x plus t times capital T1 of x minus x norm square. And now what you do is just use convexity in the usual Euclidean case. So I separate out t0 of x minus 1 minus t t0 of x minus x and t times capital T1 of x minus x. And so I get that this is by convexity 1 minus t expected value of t0 of x minus x norm square, t times expected value of t1 of x minus x norm square. So this is where I'm using Euclidean convexity of the norm square. But by my very definition, this is equal to 1 minus t W2 square rho naught to sigma plus t times W2 square rho 1 to sigma. Why is this by very definition? Because that's what T0s are. They are my Brownian map. They are my optimal transport maps. So if I evaluate this norm square, I get W2 square of rho 0 sigma and W2 square of rho 1 sigma. And so I've gotten W2 square of rho 2 sigma is bounded above by 1 minus t W2 square rho 0 sigma plus t times rho W2 square rho 1 sigma. And that gives me convexity. Good. So again, for this particular specific curve joining rho naught and rho 1, this is a particular generalized geodesic convexity. The square distance function is convex. This is a failed analogy from the Euclidean case because in Euclidean case, there is no difference between generalized geodesics and regular geodesics. They're all the same curve. And over there, you get this convexity. Okay. Convexity is very important for doing Wasserstein calculus, as we will see when we go to gradient flows. And so it's important to recover convexity of functions by considering different kinds of curves. So we will stop here today. This is what essentially the syllabus says for today, and we'll stop here. Next week, again, Professor Kim will take over. But let's see, if you guys have any questions, just ask me now. Otherwise, I'll see you, I think, in 2 weeks' time. Any questions?
Can I ask a question about the problem set?
Yes, please, go ahead.
So for the third part of the first problem, trying to show that the monotone transport is also optimal for any strictly convex
Right.
like cost function, I'm not really sure where to start with that, like what kind of direction to pursue.
Right. So that's the only difficult part of the whole problem. So I would start with trying to say that, so basically start with finitely many atoms. Start with 2 atoms. So okay, I'm going to write here. So start with 2 atoms. So supposing you have, this is my real line, and I have 2 atoms. One is these 2, and the other is the other 2. And now imagine that, so I'm doing is transport. So a monotone coupling will take this to that, and will take this to this. The other one will take this to that, and this to that. Sorry, I think I messed up. No, so this is correct. So the other one, which is the anti-monotone coupling, will take this guy to here and this guy to there. Now, for this particular one, try to prove that the monotone one is the better one. Okay. Now, if instead of 2, you have several, try to prove that if there is a cross wiring, that is that at any pair, the monotone coupling does not work, then you can reverse the cross wiring and always get a better cost of transport. Okay, that will prove it for all atomic measures. And now you use some kind of approximation to say that this must be true for all measures. Does this make sense?
Yeah, I can try that.
Yeah, this is the only difficult part in the whole problem set.
Okay. Is there a more apparent way to see for the second part that the push forward by like G inverse F of mu really does give nu? Because I ended up arguing that like it does do it for sets like minus infinity to some fixed upper bound, and then that generates the Borel sigma algebra, and then by like the monotone class theorem, I was able to argue it applies
there is a
for
much
every
easier
measurable
way.
set. But
No, there is a much easier way. This is a general fact of coming from statistics, which is that if X is any one-dimensional random variable which has a certain CDF of F,
mhm.
then F of X, this is always uniform, 0, 1. And you can just basically define this U and then prove that probability U less than or equal to T is equal to T for T between 0 and 1. Just directly trying to argue this. This is it's very simple to prove.
Oh, okay.
And then you'd see that basically every one-dimensional random variable can be mapped to uniform. And so you take one of them, map it to uniform, now apply the inverse to map the uniform back to the other guy. Then obviously you have transported one to the other.
I see. Okay. I was trying to show it directly and having a more difficult time.
Yeah.
Thank you.
So the only case where this the absolute continuity is being used, and this you'll see is to basically when can you take the uniform and get the other random variable. Okay. All right, any other
Okay, thank
question?
you.
Okay. All right, okay. If there are no other questions, have a good weekend, and I'll see you guys later. Okay. Okay.